Hi, how's it going? No camera today, it's charging, and sometimes you feel like just a minimal setup. Why not? So what we've got is we've got a whole bunch of points, and we have been drawing edges. Fair enough. But what if we want to fill those in? Well, the principle actually isn't too bad. Let's say that this shape is, this polygon that we want to draw is here on the screen. And what we essentially want to do is, fill in the lines, but also fill this in as a series, fill in a series of horizontal lines in between as well. Well, if we know the left and right x value, then we can simply draw a horizontal line. And at the moment, we're going to draw that with a solid color. We have a function that draws a line in a color, so no problem. The only issue, and it's not a big issue, is we just need to work out for every y coordinate on this shape, what is the left and right x coordinate so that we can draw those horizontal lines. So imagine that we have got an array, two arrays, one storing all the left coordinates and one storing all the right coordinates. And for simplicity, the array will cover the whole screen, but when we consume these points, we'll keep track of the minimum and maximum y value just to speed it up. But anyway, where was I? Let's pretend that our x and y points for the left and our x points for the left and right are completely reset. And as we trace a line between these 2 points, we check, okay, so we'll go from point 0 to point 1, and we'll say, hey, each of these x coordinates, are they the leftmost coordinate? Well, we'll set the array up with a default value where that will always pass. And we'll say, yep, each x point here is the smallest x coordinate we've seen, and so keep that as the left. Then we'll also say, hey, by the way, is it the rightmost coordinate we've seen? For each y value, it's the only x coordinate we've seen, so it also counts as the rightmost. Then we'll trace from point 1 to 2. We'll go along, we'll say, hey, for each of these y values, this x value, is it the smallest thing we've seen so far for that y value? We'll say yes, of course. And is it the largest thing? Yes, it is. So now we'll go from point 2 to 3. And as we trace along there, we'll say, okay, is this the smallest? No. For each y value, there is a smaller x value, which has already been registered, but it is the largest y value. What am I saying? For each y value, each of these x coordinates will be the largest x coordinate. And it's the same thing here as we go from 3 back to 0. So now these x values are overwritten, they're ignored, and we're setting it up so that we can then, for each y value between the smallest and largest, we know the left and right x point. We can set this up in a loop and draw a series of horizontal lines to fill in the shape. Okay. Simple enough. Let's have a look at it. Okay, so here we are in our project. Just the same as we always do, we'll open up the control folder, go to the app header, and give ourselves a new function. I will call this flat shading test. Okay, excellent. So we'll just head to the source file, go down to the run function, and we'll call this. Then I'll grab the clipping test, copy all of it. It's getting big. And I will remember this time to rename it. So we won't have two clipping tests, we'll have the flat shading test. There we go. Okay, so a lot of this will just be in the engine class. It won't be too hard to set this up. I'll just check through this super quickly. No, I'm happy with those points. I'm happy with those planes. Yeah, we go ahead, we transform everything. Yeah, I'm happy with that. But some things are going to have to change, so yeah. Okay. So see that I'm calling this graphics engine draw function right now with the X and Y. It's not great. So what I'll do is I'll actually get rid of that and think about it. So I have this edge table. It's a whole set of points. And what this is essentially doing is transforming the points. So let's do this. Instead of going point A, point B, we'll just do, well, I guess I'll call this point, but really it could just be point A. What I want to do is I want to loop through all the vertices in the edge table, transform each of the vertices individually, and then store them back into the table. So I perform perspective projection and then division on the point. And then what I want to do is store this back into the table. So I'll go edges, vertices, J. So I'm storing back into the original vertex. Set the X coordinate. And I'll do the same thing with the Y coordinate. And I'm not going to transform this into an integer just yet. I'll just leave it as it is. Actually, I changed my mind. Because I'm just thinking forwards a little bit. This might actually help. Okay, sorry, I'm getting lost in thought. Okay, so what this has done is it's just gone through and transformed all of the points so that the rest of the point is the same as it was before, but now the X and Y coordinate of the point is where they will appear on the screen. So now I'm going to apply a bit of lighting. I'll have a torch. And this is a directional, I'm interpreting this as a directional light. It is pointing in the positive z-axis, which means it's pointing back towards the viewer. So imagine that the viewer is shining a light on the surface, and that light is reflecting back at the viewer. So what we can then do is get the color of the face. Okay, now the way this molvec3 function works is the first argument is a vec3, the second is a scalar. So what I'm going to do is, I've missed something, haven't I? Let's go, I've forgotten to define this, so I'll just make this a white color. And then I'll scale it. So I'll take the dot product, but I want to clamp that so that it's positive. I have the normal vector, which I calculated before, so I'll just take its dot product with the torch direction. So this will indicate how parallel the surface is with the torch light, which is reflecting back at the viewer. In other words, surfaces which are directly facing towards the viewer will be brightly illuminated, and surfaces which are facing away from the viewer will be black. Okay, so what I'll do is I'll just pretend that I have this function. It's pretty much what you'd expect. So we tell the graphics engine, alrighty, I want you to draw a flat polygon. That's the name of the function. And I'm going to give it the red, green, and blue. There we go. And then I'll pass in the edge table as well. Okay, I mean, that's all you would need to draw a flat polygon. You need the color and the points. Okay, so now let's head to the engine and create this function. Just go to View, Engine Header, and down here we'll go there we go. Okay, so now what I'm going to need to do is I'm going to need to make some other functions in order to trace along each edge and store the left and rightmost x values. And just for convenience, I'll define these right now and then I'll flesh them out later. So this is what I'm going to call edge tracing. It's actually, that's also the standard name for it, edge tracing. And just the same way as we were doing with lines, we're going to have a shallow version and a steep version. So this is how it will work. We'll go so x start and x end are going to be two arrays sized to cover the whole screen, where the corresponding entry is giving the start or end value for that y value. Do you know what I mean? So if y equals 3, we would look into x start 3 and x end 3. Right, so shallow edge and then steep edge. Okay, excellent. Let's go over to the source file and define these. So we'll go to engine.cpp. There we are, down here. Okay, so edge table is undefined. Oh, it must be time to include this. So let's include linear algebras. There we go. And now we will have those definitions. All right, so this is actually going to require no drawing stuff. It'll just call other drawing functions. So let's start off with the arrays for the x begin and end. Just hard coding these sizes. We could malloc these, but malloc is a higher cost operation, so hopefully we'll get away with this. I'm also going to keep track of the minimum and maximum y values of the polygon, and I'll give them some sensible starting values so that they'll always be overwritten. So the first thing I want to do is I want to find the true min and max, the size of the polygon in the y-axis, if that makes sense. So I'll loop through all of my points in my edge table. Okay, so I'm going through each point, and then I'll do some checks. Now, I have been a little bit burnt with some of these checks, so I'm being extra careful here. So what have I got? Let's go if, look at the y coordinate. and say, well, if that's less than the current minimum, then set the current minimum. Okay, and then we'll do the same with the maximum. Okay, so now that we know the Y size of our polygon, we can set the corresponding entries for the start and end with some, again, reasonable start values. Okay, now we could use AVX to set this a little faster, but I'm just going to do it this way. So then what we need to do is for each set of edges, we'll trace along that edge. There we go. So what we're doing here is just fetching the X and Y to describe each edge. So between the jth edge and the next edge after that. So the rest of this is going to run pretty similar to drawing lines. As a matter of fact, the algorithm is the line drawing algorithm. So we need to just check whether the line we're drawing is steep or shallow. Okay, but of course, we need to make sure that we're going from the lower Y value to the upper Y value. So this is the standard case where Y1 is indeed less than Y2. But just as with line drawing, if that's not the case, all we need to do is reverse the inputs. Okay. And if this above isn't the case, then of course we have a shallow edge and we want X to go from left to right. But otherwise, yeah, it's very, very identical. Okay, so what we've done here is the purpose is to populate the array with the left and right X coordinate for each Y value. Now that that's been populated, we can run a simple loop. So we can just go, let Y be the loop variable. I think I forgot something. Yeah, it's not recognizing the other functions because we need to scope it to the class. Okay, good. Where was I? Yeah, let's do AVX to make it fast. Red, green, blue, and then we'll look up the corresponding coordinates. There we go. And that's it. That is how that function will work. It's a little long, but hopefully it's been sufficiently broken down to the stage where it makes sense. Okay, so now we need to look at tracing the edges, and this actually is very, very similar to the Bressenham algorithm. I'm going to use the Bressenham algorithm for this. Reason being, it's a little bit faster than naive. So I'll just copy all of it and then sort that out later. So where was I? shallow. Okay, right, so just scope it to the class. Now we don't need this. We don't need the frame. We don't need the color. And we do not need to clip this. That's fine. Alrighty, so here we're just setting this up so that we can trace pixel by pixel from one point to the other. And now it's inside this loop where we will do our tests. So just as a refresher, X is running from X1. I guess it should be less. Yeah, that's fine. X1 up to X2. And then we're optionally changing Y at each stage. But what we should be doing for each step, no matter what, is we should be testing the following. So we'll say if just go with it. Like I said, I've been burned a bunch of times. Weird errors like stack corruption and things. Just a manual check just to make sure. Where was I? Okay, so like I said, if this X that we're seeing right now is less than we currently have registered at that Y coordinate, then store it, of course. And same thing here. So if this X is greater than the end, then yeah, same thing. Store it. And that's it. So I'll just copy those tests. We'll go down below. It's the same business. So we don't need any of this. And then inside the loop, we'll set that. Okay, so fingers crossed. But yeah, does that make sense? So we're tracing along using the Bressenham line algorithm to go point by point between the two endpoints and check things along the way. Oh, what did I miss? Okay, let's give this a go. Well, that's not a good sign. Okay, we're getting closer. I just noticed here, I just copy pasted this, and that should be a data 1. Oh no. Okay, can you see the second error? Yeah, if the Y coordinate is bigger than the maximum we've seen, then set the maximum, not the minimum. Okay, let me just test this out. I put in a bunch of print statements and things. Let's check that it's working. Well, that is a cube. And yep, we're getting proper draw functions. Okay, we can get rid of that. And then I also got rid of the lighting calculation just to double check. Let's try this now. Oh, okay. Have I? Oh yeah, why did I do that? It's testing. Sometimes when I'm testing, I modify a whole bunch of things. There we go. Okay, cool. So as you can see, the faces which are angled towards the viewer have some, they're in full lighting, and well, it is looking up. Hello, Robot Andrew from the future, back. I just realized the issue is that this directional light is fine. It's the normal. If we go up above, the normal has been calculated. Where is it? From a straight cross product. What we can do is normalize that. So get the normal and then get it to a length of 1. And now we've got much nicer lighting. So the issue was that faces could be pointing at us a little bit and still be in full illumination. That was because the normal did not have a magnitude of 1. Anyway, this looks much better, and I'm happy to leave this now. All right, so yeah, that'll be it. Have fun, and I'll see you again soon. All right, bye.